Balasubramanian for Punctures, who's already written the title of the board, so I don't have to repeat it. It's massive sheets and rigid superconformal field theories. And we're going to tell us about that, and then if you're interested, come join us for dinner afterwards.
Okay, thanks for the invitation. I'm happy to give a talk here. So the title is Massive Sheets and Rigid Superconformal Field Theories, and it's based on a paper with the same title that appeared recently with Jacques Kessler. So I'll start my talk giving some motivation and setting up the problem. So the basic setting will be the relation between Higgs systems and n equals 2 theories. And in particular, we are interested in studying mass-deformed Seiberg-Witten geometries of n equal to 2 theories. To that end, I will introduce two definitions. These will help us get a sharp definition of the problem. So one definition will be what we call mass-like definitions. I will explain why we have the name. And then another definition will be honest mass definitions. So after giving you this introduction in sections 2 and 3, I will tell you how to basically identify mass-like deformations and honest mass deformations. So at the end, if there is time, I will give you examples and also briefly tell you about some relations to the idea of symplectic duality, but I think I may not have time to really get to that. So this is more of a realistic outline for the talk. Okay, so let me begin with the relation between Higgs systems and n equal to 2 theories. So physicists are interested in 4D n equal to 2 theories for several reasons. A sort of short way of telling you why they're interesting is they give you some intermediate case where you have some non-perturbative control and you also have some degree of rich physics behavior. Like for example, you can have asymptotically free theories, you can have conformal theories, and so on. So there's a large class of 4D n equal to 2 theories. Can be built using some certain 6D 02 superconformal field theories. These are the ones that I will talk about today. Owing to their 6-dimensional origin, these are sometimes called theories of class S, where S stands for 6. So you have more options in 6D. You can have 01 superconformal field theories, which people here study a lot. So you could use them to get even larger classes of theories. But for today's talk, I'm focusing only on these 02 theories. So there's a strategy for studying 4D n equal to 2 theories that goes back to Seiberg and Witten in the early to mid 90s. So what they proposed is, so first, before telling you that, I should tell you a generic 4D n equal to 2 theory. Let's say it's Lagrangian. In particular, let's say I'm thinking about 4D n equal to 2 theories that are superconformal. Then generically, there are at least two moduli spaces of vacua associated to these. One is what's called a Higgs branch, and another called a Coulomb branch. If I drop the assumption that this is conformal, you might have theories that don't have a Higgs branch but only have a Coulomb branch. Now, when I have a Lagrangian, It's somewhat straightforward to determine what the Higgs branch is because it does not receive what are called quantum corrections. But on the other hand, the Coulomb branch receives non-trivial quantum corrections. So the meat of the problem in solving a 4D n equal to 2 theory is in some sense determining the geometry on the Coulomb branch. So that is what Seiberg and Witten did. So in fact, what they really did is they proposed a strategy which involves combining constraints from constraints of n equal to 2 SUSY plus electric magnetic duality of the low energy theory. So by definition, the Coulomb branch is the one in which the vector multiplet scalar picks up non-zero expectation values. The Higgs branch is the one in which the hypermultiplet scalar picks up non-zero expectation values. So since the vector multiplet scalar is an adjoint valued scalar, if you give it generic expectation values, my gauge group is going to get broken down to some u1 to the r. So the low energy theory on the Coulomb branch is some interacting abelian n equal to 2 theory, and that has electric magnetic duality. It's a quantum version of the duality of Maxwell's theory. So Seiberg and Witten proposed a way to combine constraints coming from these, and they gave a way to encode the low energy effective Lagrangian on the Coulomb branch. So later works by Donaghey and Witten, Dan Freed, and also for the later paper of Seiberg and Witten, they realized that the Seiberg-Witten strategy really involves the Seiberg-Witten strategy, or more accurately, associates a complex integrable system to every 4D n equal to 2 theory. The integrable system arises in the following way. You take the 4D n equal to 2 theory, you formulate it on R12 times a circle of some radius r, and let's say I take radius to be small. Then effectively, I get a 3D n equal to 4 theory. Strictly in the r equal to 0 limit, this is true. For small r, I get something very close to being a 3D n equal to 4 theory. Now this has a Coulomb branch that is double the dimension of the Coulomb branch of the 4D theory because there are some additional scalars in 3 dimensions, some of which come from gauge fields in 4D that are sort of constant, and some of the other ones come from dualizing gauge fields in 3D. So the Coulomb branch of the 3-dimensional theory is the total space of this integrable system. So this integrable system has a total space, which I will call M3D. So there's a fibration over some base B, which is the base of this integrable system. This turns out to be the Coulomb branch of the 4-dimensional theory. Now, associated to such integrable systems are certain natural spectral curves or Seiberg-Witten curves, more appropriately in this setting, and specifying the integrable system together with this Seiberg-Witten curve and a canonical one form, which is called the Seiberg-Witten one form, encodes the low energy effective theory on the Coulomb branch. So, one of the claims to fame of these class S theories is that their associated Seiberg-Witten integrable system is nothing but a Hitchens integrable system associated to a Riemann surface C, which I will explain. So to get one of these classes theories, you start with 02 SCFT of type J, where J is a simply Layer's Lie algebra of type AD or E. I compactify this theory on some Riemann surface of genus G with n punctures, together with a partial twist to preserve as much supersymmetry as I can. So this theory has 16 supercharges. The most I can preserve after a partial twist is 8 supercharges. So generically, I would get a 4dn equal to 2 theory. The exception would be the case where C is just T2. In that case, I would actually get 4dn equal to 4. So generically, I get 4dn equal to 2. And at the punctures, we insert certain 4D defects of the 63. So these defects will be important for my talk. I will tell you more about them later. But for now, I want to emphasize that, so once you have a class S theory, then if you want to study its Coulomb branch, is controlled by some type of weighted integrable system, which in this case happens to be the Hitchin system associated to the Lie algebra G and the Riemann surface C. So what is the Hitchin system? So the Hitchin system, the total space of the Hitchin integrable system, which I will denote by MH, it's nothing but the moduli space of solutions to a set of PDEs on C. You can obtain them as a dimensional reduction of self-dual Yang-Mills equations. But for the present purposes, just take it for granted as the equations that are relevant for describing the Coulomb branch of these theories. So you have the following PDE. So it's a non-trivial observation of Hitchin that this moduli space is hyperkähler. And Hitchin also went on to show that there is a natural map, which is usually called the Hitchin map, from this total space to a base B, which is basically like for JB SLN, B is just sections of some powers of the canonical bundle, where DI are nothing but the degrees of the Weil invariant polynomials on the Cartan subalgebra. So locally, you can basically think of this map as taking the pair A, phi, where A is the gauge field whose curvature enters here, to the values of the Weil invariant polynomials built out of phi. That's basically what happens locally. Globally, you have this description that I just showed. Okay, so for class S theories, this base B, this turns out to be the 4D Coulomb branch. And this total space MH turns out to be the 3D Coulomb branch. Okay. Any questions? Okay. So far I've told you the story without punctures. I haven't told you what's happening at the punctures. Most of my talk is basically about the punctures. So let me tell you what can happen there. So the punctures are the locations where I'm inserting certain 4-dimensional defects of the 60 theory. So each 4D defect is a kind of 4D n equal to 2 system living on its own volume. It's not quite a field theory by itself, but it's some kind of 4D n equal to 2 system. Now, if I take one of these defects on a circle, I reduce down to 3 dimensions, I get a 3D n equal to 4 system. Now, luckily, this is more tractable than this gadget. This turns out to be a 3D n equal to 4 SCFT. In the literature, the SCFTs that arise this way from particular classes of defects, they're called T rho G SCFTs. I will sort of talk more about this in the second half of my talk, but I'm just giving you some idea of where I'm headed. But the crucial property here is that associated to every 3D n equal to 4 system, I can again have a Higgs and a Coulomb branch. Higgs branch and a Coulomb branch. And this Coulomb branch will enter the Hitchin system in the following way. So for my talk, I'm only going to study defects that are called tame defects. I will tell you in a moment what happens if I relax the condition of being tame. So at the punctures, so I recall I had the A field and the phi field. So I'm going to allow for simple poles for my Higgs field. So it's going to be meromorphic. This condition that it has a simple pole, that is what corresponds to the condition of tameness. If I allow for higher order poles, where this would be 1. So I'm not going to consider these, although these are extremely interesting in their own right. For today's talk, I'm focusing only on the tame case. So I have to tell you what the residue of the Higgs field is. So when I have class S, which depends on a choice of a Lie algebra and a punctured Riemann surface EGN, which a class S theory that depends on this data that happens to be a superconformal theory, then the residue of the Higgs field at each puncture should be nilpotent. So intuitively, this is the case because if this were not true, then I would have some non-trivial Jordan decomposition where there's a semi-simple part and maybe a nilpotent part, and the eigenvalues of the semi-simple part would set some kind of scale in the theory. And since I want something that's superconformal, I want something that has no scale. So that's why this condition comes about. So these are the cases that correspond to superconformal field theories. So the case with wild punctures works a bit differently, but let me not get into that. Okay. Okay, let me write out one particular formula that is useful. So I want to give you the formula for the total space of the Hitchin system in the presence of a bunch of punctures. there is a global contribution, which is just dependent on the genus and the choice of the group. I should really write J here. Yeah, let me write J. And there's a sum over the punctures where OI is the adjoint orbit in which the residue of phi at the puncture I lives. So what matters really is not the element itself, but the orbit in which it belongs, because that's the invariant data of Lucci conjugacy. So I'm writing out this formula because when I start mass deforming the superconformal field theory, I want a deformation that preserves this dimension, because otherwise I would have some kind of awkward jumping behavior. So let me now give you my definition. So our goal is to study mass deformations of 4D n equal to 2 class S theories. So in general, you want to study mass deformations of superconformal field theories because once you understand the Seiberg-Witten geometry of a mass deformed superconformal theory, you can take various scaling limits and you can get new Seiberg-Witten geometries out of it. For example, already back in the 90s, Seiberg-Witten showed that if you understood the mass deformed geometry of the SU2 theory with 4 fundamental flavors, which is the superconformal case, you can use that to infer the Seiberg-Witten geometry for the case with n of equal to 0, 1, 2, 3, or 4. So in some sense, this is the smartest of the lot. Once you know the answer to this, you can get the answer for all of these. So that's the motivating reason. So this is the goal. So towards this goal, I'm going to make 2 definitions. The first definition is what we call mass-like deformation of Hayem-Hitchin system. So I want a mass-like deformation to obey the following conditions. So this is any deformation that obeys. The first condition is that the dimension of the adjoint orbit before the deformation should be the same as the dimension of the adjoint orbit after the deformation. That's one condition. That's why I sort of wrote this formula for you, because the dimension enters the dimension of the total Coulomb branch. The second condition is that if I look at the holomorphic symplectic form on the deformed Coulomb branch, so I'm talking here about mass deformations of the 3D n equal to 4 theory. So that is mass deformations of the total space, which is hyperkähler. In particular, it's holomorphic symplectic. So it has a CP1 family of holomorphic symplectic forms. Let's say I fix some complex structure J. I look at the holomorphic symplectic form in that complex structure for non-zero mass parameters. If I look at that, that should vary in some very simple way. It should just depend linearly on the masses. So mass deformations are some kind of flat deformation, which just scales the holomorphic symplectic form.
Can you just read what it says?
This one?
Omega, so
in complex structure J, for non-zero masses, it should just scale linearly as masses.
what's this supposed to be?
non-zero masses, m not equal to 0. Okay. So in particular, in the limit where m goes to 0, I should retrieve the holomorphic symplectic form on the nilpotent orbit. And in this limit, I don't want the rank to jump, but that's basically covered in this condition. Okay? So I will call any deformation of the integrable system that obeys these properties to be a mass-like deformation.
This definition presupposes that the deformation is as a symplectic leaf in the Poisson space of Higgs branches, because we're talking about residues and coherent orbitals.
Yes, yes, yes.
So you're just asking which deformations as a symplectic leaf are the mass-like ones.
Yes.
Well, but then why isn't the second condition just a corollary of Dec4?
Indeed, so it is a corollary of that. So as long as I do this, well, okay, so I haven't told you yet how I'm changing the residue. If I change it in some nice enough way, that's a consequence of residual mapping. So in fact, I should emphasize here that the motivation for our strategy goes back to a paper of Donald and Witten. It's the same paper that I cited earlier in the 90s, where Ron and Witten, they studied the Hitchin system for the SUN, what's called the n equal to 2 star theory. That's a particular Hitchin system that corresponds to a torus with a single puncture with a particular ramification data here. And they were studying the theory for non-zero mass deformations, and we were sort of adapting that strategy for more general cases. Okay, so this is my definition of a mass-like. This is my definition of a mass-like deformation, but this is not quite a mass deformation. Okay, I need more space. For it to be an honest mass deformation, I need one further property to hold. So associated to each defect has, it is a flavor symmetry that's actually not obvious on the Coulomb branch. It's really more obvious on the Higgs branch. I haven't told you how to associate a Higgs branch to one of these 10 defects. So at the moment, sort of take this as something that exists. I will try to say more a bit later. But this is some complex Lie algebra F. So for now, you can think of it as a subalgebra of the Lie algebra J that I introduced. Now, honest mass deformations but okay, maybe I'll just say one word about how this enters. So I introduced these theories that are called T, rho, J theories. They're associated to a single tame defect. They have a Higgs branch and a Coulomb branch. These flavor symmetries basically act as isometries of the Higgs branch, while what I'm trying to deform is actually the Coulomb branch. But there is a condition that sort of ties these two together that comes from superconformal representation theory. This is, for example, summarized nicely by a recent paper of Cordova, Dumitrescu, and Intriligator. So what this tells me is that these mass parameters Mi should also live in the cartan of this flavor symmetry that acts on the Higgs branch. So this is what we call the flavor condition in the paper. So this is in addition to those two conditions. So basically, the definition of a mass deformation is that mass deformations are those mass-like deformations that obey the flavor condition.
Can you say what these J and F are in terms of the Higgs system?
So,
I mean, since you are putting the condition of the Coulomb branch directly, there has to be a way of saying what they are in terms of the Coulomb branch.
right. So for what I called maybe wait till I go over the next section. I think it will become a bit more clear. Okay. So one of the features of this problem is that the flavor symmetry itself is not obvious on the Coulomb branch, but what will be obvious is if I deform the Coulomb branch, then there will be some space of deformation parameters, and on that, the wild group of the flavor symmetry will act in some natural way. So that's the way it will show up on the Coulomb branch.
I'm confused whether the defects and punctures are the same or different.
So I put a defect at each puncture.
But you said you wanted to have only one single defect? I thought you had a bunch of punctures.
No. So there's a bunch of punctures in general, but there is one of these T-row theories for each such defect. There is one such T-row theory for each defect. So if I have a whole bunch of punctures associated to each of these, there are T-row J theories.
So that's not the picture you were drawing from the earlier with a node that look and node is supposed to the punctures. They're not getting that.
No, there are no nodes.
No.
There are no nodes. Okay. So now I'm ready to move on to the next part of my talk. So in this part, I want to tell you how to classify all mass-like deformations of the Higgs system. To do that, I want to introduce a notion called a sheet. This may not be familiar to everyone, so let me take a few minutes to introduce what a sheet is. So take any complex Lie algebra, let me just denote it by G. So far I was dealing only with simply laced cases. So they correspond to what are called untwisted defects. So you can also study what are called twisted defects, which correspond to taking one of these simply laced Lie algebras but doing some kind of outer automorphism twist to get a non-simply laced Lie algebra. So the twisted defects of the 6D theory end up being classified by nilpotent orbits in non-simply laced Lie algebras. So henceforth, I will use the letter G to denote Lie algebras with the understanding that G can be non-simply laced, while my J originally was only simply laced. So let me talk about sheets in an arbitrary complex Lie algebra. So I look at adjoint orbits of some fixed dimension, T. I always write complex dimensions. So look at the union of all of them. Take the union of all such orbits. Let me call this space U of T. So in general, that's some complicated space. I take irreducible components of U of D. Those are what are called sheets. So it's a natural thing to study in structure theory of adjoint orbits and representation theory. So let me tell you how sheets look by giving you the most basic example. In SL2, you have, of course, the zero orbit, which is the unique zero-dimensional type. That's a sheet by itself. That's sort of boring. But you also have, so let's say this is a generic SL2 element. If it has determinant 0, then this corresponds to a nilpotent orbit. It has complex dimension 2. You could also have a semi-simple orbit where A is some C star element. That corresponds to, again, semi-simple orbit of dimension 2. So you take the union of the nilpotent orbit and all the semi-simple orbits, is an infinite number of them, that gives you a sheet. That's the only non-trivial sheet in SL2. So you can do something similar for all the other Lie algebras. So let me tell you some properties of sheets. So the first thing is that there's always a finite number of them in any complex Lie algebra. The second thing is that there's always a unique nilpotent orbit in a sheet. And that is basically the orbit that you get by scaling the non-nilpotent guys by some C star action and taking its fixed point. That will be a unique nilpotent orbit. Now, in type A, G is an end, every nilpotent orbit occurs in a unique sheet. But this property can fail in other types, and that leads to much interesting structure. More generally, if you want to classify all sheets, you do the following. So the schematic picture of a sheet is that at its boundary, so I have something nilpotent. So I will denote that by some orbit O of A naught. Away from the boundary, I have some element which I will call O of A tilde. You take one of these guys, you do its Jordan decomposition. So we are in the Lie algebra, so this is an additive Jordan decomposition. I want that these two compute. Now, to parameterize a sheet, what I do is I look at its semi-simple part. I look at the centralizer in G of this semi-simple part. That is going to be some Levy subalgebra. I will call it L. Now, you can check that the remaining nilpotent guy here, you can think of it as a nilpotent element in this Levy subalgebra because of this condition. So what I do is to remember the sheet, I remember this Levy together with this nilpotent in that Levy. So this is a way to parameterize sheets. Now, you can sort of do this inductively.
The twiddle guy is the orbit of the nilpotent in the Levy?
Yes, the twiddle guy is the orbit of the nilpotent in the Levy. So you can do this inductively until you hit things that are called rigid nilpotent orbits. They are the ones who don't have a nearby non-nilpotent orbit of the same dimension. So the classification really boils down to listing pairs of levies together with rigid nilpotent orbits in the levies. So if you do this classification, you find that sheets come in basically three types. There are two types of sheets. The first type is what's called a Dec4 sheet. These are sheets that contain semi-simple elements. So in other words, if I were to go to some general point on the sheet, I take one of its elements and do Jordan decomposition, I get a Jordan decomposition where this nilpotent part is 0. So these would be the ones that have sheet labels of the form Levy, 0 are the sheet labels for Dec4 sheets. At the other extreme end are rigid sheets. These are sheets that contain a single nilpotent orbit. So their label will be of the form G, O, where O is a rigid nilpotent orbit. An example of a rigid nilpotent orbit is the minimal nilpotent orbit in every Cartan type other than A. So by minimal, I mean the smallest non-zero nilpotent orbit. So that's always rigid. Now there's an intermediate case, which are just mixed sheets. Basically, you have non-nilpotent guys, but they're not semi-simple. So this is the most general case. So you have these three types of sheets, and you can explicitly write them down. Basically, nilpotent orbits in every Lie algebra are classified. You can look up Collingwood and McGovern. So you take that classification and you try and see what are the sheets attached to each of these nilpotent orbits. So it's a finite problem. Once somebody gives you a Lie algebra, you can write out all the sheets in that Lie algebra.
So your condition 2 is just a condition that the subspace in the sheet that parameterizes the deformations is affine linear in the ambient Lie algebra.
Yes.
And condition 3 is that it's a Cartan subalgebra.
So I haven't imposed condition 3 yet. Good. Thanks for keeping track. So the first main result of our paper, which is really putting together of different things. So it could have been done long before our paper. I think it just wasn't written in this way. So the first result is that mass-like deformations of the Tame-Hitchin system are completely classified by sheets attached to the nilpotent residues. So by a Tame-Hitchin system, I'm thinking of a Tame-Hitchin system in which all the residues are already fixed to be particular nilpotents. So if I want to classify all mass-like deformations of it, so you just go to each of the punctures, look at the nilpotent orbits, look at all the sheets on which they lie. That's a classification of all your mass-like deformations. Now, this does not give you a mass deformation every time because I have not imposed the Kleber condition so far. So let me try to tell you how to do that.
I'm confused again. Is this a one puncture story or many punctures?
I can have many punctures, but the problem is essentially at a single puncture. If I solve that, I can do it at every puncture. I'm now doing this, well.
So you have separate mass parameters for each puncture?
Yes, I have separate mass parameters for each puncture. Yeah. Okay, so let me tell you how the flavor symmetry enters. I have maybe 10 minutes.
At least.
Yeah, okay. Okay, so let me recall the fact that associated to every Tame defect, if I put it on a circle, I get the 3D n equal to 4 theory that in the literature it's called T rho of G. So I'm again switching to using G with the understanding that whenever I use G, I'm allowing for non-simply laced cases. They correspond to what are called twisted defects of the 6D theory. So although I had only a choice of a simply laced Lie algebra in 6D, it makes sense to think of twisted defects for which the underlying 3D n equal to 4 theory would be T rho G, where G is non-simply laced. This is explained more carefully in the introduction to our paper. Okay, so this guy has a Higgs branch and a Coulomb branch. So when I mass deform the 3D, mass deforming this theory implies, on the one hand, I lift some directions in the Higgs branch, and I also deform the Coulomb branch. Now, it's a fact that I will just tell you, to take my word for it, that the Higgs branches of these theories are certain spaces that arise as slices to nilpotent orbits. So let me tell you how they arise. So there's a label rho here, which I introduced, but I haven't told you what it is. So rho is SL2 embedding in the Lie algebra G. Associated to this SL2 embedding is an orbit ON, which is a nilpotent orbit in G. This association is by the Jacobson-Morozov theorem. Now, the Slaughter slice to this orbit is basically defined in the following way. So I have the standard SL2 triple, the Solomon slice to the orbit ON. Basically, is you take the nil positive element and you add the centralizer of the nil negative element. And the Higgs branch here is basically this Solomon slice intersected with the nilpotent cone of G. This comes about as some moduli space of solutions to some noun equations, but let's just take that for granted. On the other side, the Coulomb branch, this happens to be the closure of a particular nilpotent orbit. And it turns out that it's more naturally in G dual, where G dual is the Langlands or G and O dual of the algebra. Now this is the guy that enters the Hitchin system. This enters the Hitchin system. So although I've been sort of been writing Hitchin systems for G, more naturally in the notation that I currently have on the board, what I really get is Hitchin systems for G dual. So when I turn on mass deformations, I'm trying to deform this nilpotent orbit to being something non-nilpotent, but I also have this condition that Mi should live in the Cartan of this flavor symmetry. So what does the flavor symmetry do? So first of all, the flavor symmetry is defined in terms of the Higgs branch data in the following way. It's nothing but the centralizer in G of the entire SL2 triple So note that this is defined purely in terms of Higgs branch data. So this condition is something that pairs a property of the Coulomb branch, its space of deformations, with some property of the Higgs branch. So it's not something that's visible if you're just studying the Hitchin system for G dual. It's something that necessarily comes from physics. It ties together the Higgs and the Coulomb branch data. So the strategy is, if somebody gives you one of these theories, or equivalently one of these defects, if you know it's Higgs and Coulomb branch, you go look at its Coulomb branch, it's some nilpotent orbit, you list out all the sheets on which that nilpotent orbit lives, then you come back and check which of the sheets obey this flavor condition. So you observe that there's always a unique solution. And that is the sheet that we would call as the mass deformed Coulomb branch. Okay? Since I'm running short on time, let me quickly tell you how the answer looks. So I will assume some familiarity with structure theory of nilpotent orbits. I'm happy to expand on this after the end of my talk. So this is my Higgs branch nilpotent orbit. Now associated to this is something called its Bala-Carter-Levy subalgebra. So if you do not know what this means, just take for granted that it exists. There's a standard algorithm that you can look up to compute it. So let me denote that by LPC. Now you take the Bala-Carter-Levy corresponding to this non-nilpotent orbit, then you go and look at all the sheets attached to the Hitchin orbit. There's a unique guy for which there's always a unique sheet. In some cases, it might be a subsheet, but let me ignore that for the moment. There's always a unique sheet such that the sheet Levy which is really a Levy subalgebra of the Langlands dual Lie algebra. That happens to be the Langlands dual of this Bala-Carter Levy. So our claim is that this identifies the Mars-deformed Coulomb branch of this TV rho G theory. Okay, so this is the general theoretical framework. Let me quickly give you some examples so that you have some intuition for what is happening. So in type A, all of this is a bit of an overkill because each nilpotent orbit occurs in just one sheet. So if I tell you that the Coulomb branch is a particular nilpotent orbit, then I've also automatically told you how to deform it. But already if you go to D4, nilpotent orbits in D4 are classified by partitions of 8, but not all partitions occur, only what are called D-type partitions occur. These are partitions where even paths occur even number of times. There's a particular nilpotent orbit which is 3 squared, 1 squared. It turns out this occurs at the boundary of 2 sheets. One has sheet Levy being A1 plus D2. D2 is of course 2A1, but I'm writing it in a way that generalizes to higher rank. The other sheet is A2, 0. So if I gave you a Hitchin system in which the Higgs field has nilpotent residue in this orbit, and I tell you that I have to mass deform, I haven't given you enough information because you could go on this sheet or you could go on this sheet. So there's some degeneracy that needs to be broken. It turns out this happens because there are actually 2 T rho theories. One of them corresponds to T rho being 3 squared, 1 squared, and the other corresponds to rho being 3, 2 squared, 1. There are these 2 theories. The Higgs branch of this is the slice to this orbit. The Higgs branch of this guy is the slice to 3, 2 squared, 1. I always mean the slice intersected with a nilpotent cone. Now it turns out the Coulomb branch of both of these guys is the same nilpotent orbit 3 squared, 1 squared. But if I mass deform this, that corresponds to the A20 sheet, and the mass deformation of this corresponds to the A1 plus D2 sheet. You can check that these are precisely the Bala-Carter levies of these 2 orbits. Langlands duality doesn't matter here because I'm in D4, so I just land back on D4. So every such case where you have different defects that sort of have different Higgs branches, but they share a Coulomb branch, their mass deformations always fit into this pattern. So that's a highly non-trivial statement. This never happens in type A because this sort of structure never happens in type A. Now, more generally, we don't get all sheets in this fashion. We only get what we call our special sheets as mass deformed Coulomb branches. This is a case-by-case observation for us, but it's a highly non-trivial observation.
What does this mean? So you're saying that there is the same nilpotent orbit that belongs to many sheets, the boundaries of many different sheets,
Yes.
and only certain of them are selected by the flavors?
Yes. Yes.
So there are sheets for which no flavor actually gives you that deformation.
Yes,
mass
absolutely,
deformation.
absolutely, absolutely, yes. So this is a corollary is that non-special sheets are not mass deformations of T rho G theories. There might be mass deformations of some other 3D n equal to 4 theories. I don't know how to rule that out, but they're definitely not mass deformations of these guys. I think this is an independent, interesting observation. So I can't really do justice to symplectic duality, but let me say in a few short words that a physics interpretation of symplectic duality is about how Higgs and Coulomb branches get paired up for particular 3D n equal to 4 theories. Justin can tell you a lot more about it, but for this particular T rho G theories, so we are seeing that there's a pairing between slices on one side, which are the Higgs branches, and sheets on the other side, which are the deformed Coulomb branches. So we believe that's the natural way to think of symplectic duality at the level of the moduli spaces themselves. In particular, we conjecture that only special sheets occur as symplectic duals to slices. These non-special sheets somehow don't occur as symplectic duals. Okay, I think sort of, yeah, 4 minutes over time. I'm happy to answer questions, but I will stop here. Okay.
Special just means that it arises.
Okay, good. I didn't tell you what it means. So special means that in this pair, I only told you that this guy is always the Langlands dual of Bala-Carter. I didn't tell you what this is. It turns out this is always a special nilpotent orbit in this legging. So here I'm alluding to a definition of special that goes back to Lustig. He defined a class of special nilpotent orbits, but for us it's more natural to think of specialness as a property of the sheet itself, because there are some peculiar cases where you can have a non-special sheet whose boundary is a special nilpotent orbit. So you could have one such L theta where this is special, but if you go to the boundary, you get something that's non-special. Oh no, sorry, it's the other way around. It's the other way around. You could have non-special sheets whose boundary is a special nilpotent orbit. So such instances do not correspond to mass deformations for us. So that's why we sort of think of specialness as a property more naturally of the sheet itself. But it does rely on Lustig's definition of specialness. There is a independent way to think of special orbits, which corresponds to studying associated varieties of some primitive ideals in the universal enveloping algebra. I believe the statement is that only special orbits occur as associated varieties of primitive ideals. That's a result due to Barbash and Vogel. Okay, thanks so much.